So we're in section 2.5, and we're talking about zeros of polynomials. Some additional tools we can use to find zeros of polynomials. And the big result that we can finally state now that we've talked about complex numbers, we've talked about different ways of solving polynomials. We know what a polynomial is. We can state the fundamental theorem of algebra. And anytime you get something that's called the fundamental theorem, it's a good clue that it's something pretty important. So the fundamental theorem of algebra tells us that if f of x is a polynomial, a polynomial of degree n, where n is greater than 0, then f has at least one zero in the complex number system. Right. So if we have a polynomial, we know any polynomial is going to have at least one zero in the complex numbers. And let's remember we said a polynomial was we could write f of x equals a sub n x to the n is our degree, plus we have a bunch of these terms, a sub n minus 1, xn minus 1, and we keep adding terms until we get to a sub 1 x plus a sub 0. So that's a polynomial. N is our degree, is the highest exponent, and it tells us that we have at least one zero in the complex numbers. Now, a real number is still in the complex numbers. So remember, a complex number is something in the form a plus bi. So if b is 0, we still have a complex number. We have a plus 0i. So a real number is still part of the complex number system. So the fundamental theorem of algebra includes the complex numbers, include the real numbers. And what it's telling us is that we're going to have at least one zero. Now let's think of a function. Let's just talk about a couple of functions like y equals x squared. What is the zero? What are the zeros of y equals x squared? Where is y equals 0? What value of x makes y equal 0? 0. X equals 0 is a 0. And because we, in order to solve this, we say x squared equals 0. So we take the square root of both sides, and we say plus or minus x equals 0. So this 0 is a root with multiplicity 2. So according to the fundamental theorem of algebra, we would say that this this equation has two zeros. They just both happen to be 0. So the important part of the fundamental theorem of algebra is that it tells us that if we have a polynomial, we can always find a solution. There's some solution that we can find. And we're interested in how we find that solution. Now, something that follows from the fundamental theorem of algebra is called the linear factor theorem. The linear factor theorem says that if we have a polynomial function, just like we talked about in the fundamental theorem of algebra, and our degree is n, where n is greater than 0, we can factor into n factors. I'm going to write an if here. If f of x is a polynomial of degree n where n is greater than 0, then f has exactly n factors. And by linear factor, we mean something like x minus 2, x minus 3, x plus 2. Those are linear factors. So what this is telling us is that f of x we can write as a sub n times x minus c1 times x minus c2 times dot 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 times x minus Cn, where C1, 2, 3 are complex numbers. So this just tells us if we have degree n, we can factor our polynomial into n terms that look like this. And our factors are x minus some complex number. If our imaginary part of our complex number happens to be 0, these would be the C1, C2 could be real numbers. Real numbers are still part of the complex numbers. So the linear factor theorem is important because it tells us that we can factor a polynomial completely into linear factors. So if we have a third degree polynomial, we can factor it into 3 parentheses. If we have a fourth degree, we can factor it into 4 parentheses. We've been working with quadratic equations where we end up with 2 parentheses, but any polynomial we can factor it into n parentheses if its degree is n. And remember, when we have a factor, that's the same way as saying C1, C2, dot, 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 Cn are solutions of f of x equals 0. And it's also the same as saying C1, C2, dot, 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 Cn are zeros of f of x. Factor, solution, 0 all mean the same thing. So these two theorems, the fundamental theorem of algebra and the linear factor theorem, are what are called existence theorems. They tell us that these solutions exist, these factors exist. They don't tell us anything about how to find them. We know they exist, so we need to figure out a way to find them. And that's really what we're interested in this section, is how do we find these zeros? We know they exist, how do we find them? So the next couple of things that we're going to do are ways, additional ways to help us find zeros. Any questions before we move on? All right, so we know these factors exist. We know these solutions exist. So we want to be able to find them. The first tool that we use is called the rational zero test. And this test is going to be very important. It's a powerful tool to help you find zeros. So our rational zero test tells us that if a polynomial, we have a polynomial, f of x equals, and I'm going to write this down, again, a sub n x to the n plus a sub n minus 1, x to the n minus 1, plus dot dot dot, plus a1x, plus a0. If this polynomial has integer coefficients, a sub 0, a1x plus a sub 0. That's just our last number there. If this polynomial has integer coefficients, let's remember what an integer is. Anybody remind us what an integer is? What kind of number? Negative, zero, or positive, and they are whole numbers. So negative 1, negative 2, negative 3, 1, 2, 3. So those are integers. So our coefficients are integers. So none of the a's are fractions. They're integers. So if this polynomial has integer coefficients with a sub n, a sub n not equal to 0, and a sub 0 not equal to 0. So the first one and the last one are not 0. Then any rational 0 of f, and this sounds more complicated than it really is. Any rational 0 of f will be in the form p over q, and let's remember what a rational number is before we go on. A rational number is a fraction of integers. So p is going to be a whole number, negative 1, negative 2, negative 3, da 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 da, 1, 2, 3, and q is going to be a whole number. So if we have a rational 0, if a solution to this polynomial is a rational fraction, so it's not a decimal that repeats forever, it's some nice fraction that's made up of integer on the top and integer on the bottom. So any rational 0 will be of the form p over q, where p is a factor p is a factor of a sub 0, and q is a factor of a sub n. So any solution to this polynomial that's a rational fraction, the numerator has to be a factor of a sub 0, and the denominator has to be a factor of a sub n. So that limits what the solutions of your polynomial can be. So that gives us a list of possible solutions so that we can eliminate some possibilities right off the bat. Because if we look at a polynomial, we would have no idea. If we have a complicated polynomial, we wouldn't know what a possible solution would be. So this helps us eliminate some. So let's look at how we use the rational zero test. So we have, let's say we want to find the zeros. Of x cubed minus 7x minus 6. So we want to find the zeros. Now, if we were to go about, if you were just given this problem, you didn't know anything else, how do you think you would go about finding the zeros of this function? Yeah. What's that? Put it in parentheses, so you want to try to factor it somehow. So we want to factor it. If it's a difficult one to factor, so a factor is one way we could find the solution. If it's difficult to factor, that could be hard. What's another way we could find the solution of this? Anybody have an idea? How about a calculator? Could you graph it and see where it crosses the x-axis? That would give you the zeros. So that would give you an approximation of the zeros. So you could graph it. You could look at a graph. So that would be another way. We want to look at this analytically. How can we find it? How can we find these zeros without using a calculator, with just what we know about functions and the zeros? Yes?
On the
quiz and test is no calculator. So we're going to use the rational zero test here. So let's list the factors of a sub 0. A sub 0 is -6. That's our last number. So our numerator of our possible zeros, possible rational zeros, so P, the numerator of our possible rational zeros, could be any factor of 6, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are the factors of -6. We want numbers that divide 6 evenly. Okay? And Q, a sub n equals our first number in front of our highest power. So a sub n is 1. So Q is just plus or minus 1. So our possible rational solutions are any fraction we can make with P over Q. So those are just plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are our only possible rational solutions. So this gives us a list of numbers that we can use to start finding our factors. Now we have 1, so we're just going to test some of these. And if we know that these are a possible factor, how would we test if they're a factor of our function? Cedric? Synthetic division. And if they're a factor, what happens with synthetic division? The remainder is 0. So with synthetic division, we test a factor and we see if the remainder is 0. Now with 1 is usually pretty easy to test. Plus and minus 1. So if I plug 1 in here, I can just test that. F of 1 is 1 minus 7 minus 6. And that does not equal 0. What's that? I'm just testing. I'm just going to see if, because 1 is easy to plug in, I'm just going to test to see if 1. I'm just going to test it in the function, because 1 is usually pretty easy to evaluate. 1 and -1 in a polynomial, as long as we don't have a lot of terms. F of -1 If I plug in -1, I get -1 plus 7 minus 6 equals 0. So I know that -1, x equals -1, is a 0. So what is our first factor going to be of this polynomial? If x minus 1 is a 0, what's a factor? X plus 1 is a factor. So x plus 1 is a factor. I can write this as x minus -1. So -1 is my 0, so x plus 1 is a factor. So now I'm going to use synthetic division to simplify this. I'm going to use synthetic division with -1. So I'm going to put a -1 here, and I have a 1, -7, -6. 1 times -1 is -1. -7 and -1 is -8. Oops, I forgot my x squared. That's what you were talking about, right, Cedric? So we need our 0 for my x squared term. 1, 0, -7, -6. I have a 0 for my x squared term. So I get -1 here. Add those, I get -1. I get a +1 here. -7 plus 1 is -6. I get a +6, and my remainder is 0, just like we thought. So my factors, I have, so f of x is x plus 1 times x squared minus x minus 6. That's what I get. That's what I'm left with after I do synthetic division. And we can factor x squared minus x minus 6.
Wait, so how did you get the x squared minus 6, or minus x minus 6?
When I divided this polynomial by x plus 1, what I'm left with is 1x squared minus x minus 6. That's what these numbers tell us when I do synthetic division. So how do I factor x squared minus x minus 6? X minus 3, x plus 2. So these are all my factors of f of x. If I multiply this out, I would get this. And my solutions are x equals -1, x equals 3, and x equals -2. Those are the three solutions to my original function.
So that's the answer.
So this is the linear factorization. So if the problem asks you for the linear factorization, it's asking you for this. And if it asks you for the zeros, these are the zeros. So in finding the zeros, in finding the linear factors, you're doing the same thing. The linear factors can give you the zeros can give you the linear factors. Questions on that? Let's look at another example. So let's say we want the zeros the zeros of 3x to the third minus 20x squared plus 23x plus 10. So we want all the zeros of this function. So a sub 0 is 10. So p, our numerator of our possible rational zeros, are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. A sub n equals 3. So q, the denominator, can be plus or minus 1 or plus or minus 3. Those are the only possibilities. So our possible solutions. Our possible solutions are plus or minus 1. We have quite a few. Plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, and plus or minus 10/3. Our possible solutions are p divided by q. So all the possibilities of p divided by all the possibilities of q. So any of these can be the numerator, and any of these can be the denominator. So these are the possible zeros of this polynomial. So let's eliminate. Let's see if we can eliminate a couple. Let's try, because we just have a third degree polynomial, f of 1 and f of minus 1 aren't that hard to calculate. F of 1, if I just plug in 1 for x, is 3 minus 20 plus 23 plus 10, which is not 0. So 1 is not a 0, so we can eliminate 1. Let's try negative 1. We plug in f of negative 1. We plug in negative 1 for x. I get a negative 3 minus 20 minus 23 plus 10. X is minus 1. So minus x minus 1 times 23 is minus 23. X squared, if we square negative 1, we get a positive. So this doesn't change that negative. So this doesn't equal 0. So 1 and negative 1 don't give us a 0. So let's test the next one with synthetic division. We're going to try...
question.
Yes.
So, like, how do you find the possible solutions?
The numerator are all the factors of my last number here. All the numbers that divide 10 evenly. My denominator are all the numbers that divide this first number evenly.
So
So that's the rational zero theorem tells us that the solutions, the possible solutions, are any of these fractions. And we want to test the easy ones first. So I tested positive 1, negative 1. So let's test. We're going to use synthetic division to test another one. So let's test x minus 2. So we're going to test x minus 2. So we're going to use synthetic division with 2, and we're going to put 3 minus 20, 23, and 10 here. So I get 6. Negative 20 plus 6 is negative 14. 2 times negative 14 is negative 28. 23 plus negative 28 is negative 5. 2 times negative 5 is 10. So 2 is a solution. I get a remainder of 0. sorry, yeah, that would be negative 10, and when I add, I get 0. So our remainder is 0, so 2 is a solution. So x minus 2 is a factor. So f of x is x minus 2 times 3x squared minus 14x minus 5. That's what I'm left with. Well, according to our linear factor theorem, how many factors does this polynomial have? 2, because my highest exponent is 2. So I have 2 more factors. So this is x minus 2, and I can factor this quadratic. I get 3x and x. The only factors of 5 are 5 and 1. So I can factor this as negative 5 and positive 1. The other way we could solve this one is by the quadratic formula, or we could test another 0 from the list using synthetic division. Well, because we had a quadratic, we can factor it into parentheses. So my zeros, are x equals 2 from this parentheses, x equals negative 1/3 from this parentheses, and x equals 5 from this parentheses. So these are my zeros. Questions? Now, if you have a big polynomial, if you had a 5th degree or a 6th degree polynomial, or if you have a lot of factors, if these numbers, the a sub n and the a sub 0, are big, you could end up with a long list. Most of the problems that you're going to work on have a pretty short list, and they're pretty easy to test. Let me give you one last piece of information, and then we'll stop for today. And then I'll briefly tomorrow I'll give you one other thing that can help eliminate some of these numbers. But for now, this is what we need to what we'll work with. All right, the last piece of information is conjugate pairs. So let's remember, what is a conjugate? If we have a complex number a plus bi, the conjugate equals what? A minus bi. We change the sign on the imaginary part. So the reason we need to know about conjugate pairs is if f of x is a polynomial with real coefficients, that's just telling me that all the a's are real numbers, the a sub n, a sub n, x to the n, all those numbers are real numbers. And a plus bi is a solution. A minus bi is also a solution. So if we have a complex solution to our polynomial, the complex solutions always occur in conjugate pairs. So if you think about solving a quadratic equation with the quadratic formula, and you get negative b plus or minus the square root of b squared minus 4ac all over 2a, that plus or minus is what gives you, if you get an imaginary solution, that plus or minus is what gives you the conjugate. You get one solution for the plus and one solution for the minus. So your complex solutions are always going to occur in conjugate pairs. So the way the problems that you're going to see that have to do with this idea, well, one, if you know that if you have one complex solution, the conjugate is always going to be also going to be a solution. But the problems that you'll see would be something like, let's see, we want to find a fourth degree polynomial with our zeros as 0, 1, and I. So we want to find a fourth degree polynomial with zeros 0, 1, and I. If I is a solution, and we know that our solutions occur in conjugate pairs, then negative I is a solution also. And if we have our zeros give us our factors. So one way we could write this polynomial is that f of x equals x minus 0 times x minus 1 times x minus I times x plus I. So my factors are going to be just x minus my zeros. So this would be one way we could write a fourth degree polynomial, and then I can multiply this all out to come up with a fourth degree polynomial. If I multiply this out, I get x to the fourth minus x to the third plus x squared minus x. So that would be my one example of a fourth degree polynomial that has these four solutions. I just take my solution, my factors are x minus the solution, multiply those all together in parentheses. But the important thing to remember here is that if you have a complex zero, that the conjugate is also a zero. Any questions? Okay, let me give you your homework. Again, our quiz is on block day. We'll review tomorrow. So we'll have a little time to review. All right, there you go.